Muted.
Hello, everyone, and welcome to April's Astronomy on Tap. I am your host, Courtney, and this month we're coming to you live from Baton Rouge, but as per it has been for a while, we're still using this opportunity to give you some really great speakers from across the world since we're still online for now. And this month we have two graduate students to give talks, both of whom are actually Astrobytes authors. So if you're curious, you can go check them out on Astrobytes and read all their little blurbs and stuff. Before we get started, here are the usual ground rules. First off is to be considerate in the chat. We've never had any issues with this, but it's good to always say it. Second off, feel free to drop your questions for the speaker at any point during the talk into the chat, and I will field them to the speaker after the talk is over. Third thing is to please consider donating to our Venmo and PayPal. That's what lets us keep going with these shows, and so we're always happy to have that. And as per usual, we like to add some competition to our donations. So this month, we're asking you which of the famous Collins you like better. Do you prefer Phil Collins or do you prefer Michael Collins? Now, if you're not familiar, Michael Collins was on the Apollo 11 mission, which did land on the moon, but he had the honor of staying in the capsule while Buzz Aldrin and Neil Armstrong got to step on the moon. Now, Phil Collins, on the other hand, he was the drummer and singer for Genesis, the composer of the banger of a Tarzan soundtrack, and performed the hit single In the Air Tonight. So we want to know, which one do you prefer? If you make a donation, please be sure to write your answer in the memo section of that donation. That will help us keep track of your vote. And lastly, please like this video if you're watching and subscribe to our YouTube channel. Both of those things help us out so much more than you would think they do. And without any further ado, I'm going to move right on to today's talks. So first off, we have a graduate student currently at Stony Brook University. As I mentioned earlier, she is a writer for Astrobytes, but she also writes her own music, which you can check out wherever you normally listen to music, Spotify, Apple Music, wherever. She's here to tell us today about planet formation theories. I would love to welcome Sabina Sagynbayeva.
Hi everyone. I'm really happy to be here and I'm really happy to talk about planet formation. I really hope that you all do great and you're all vaccinated. So let me share my screen. So yeah, let's talk about planet formation. So planet formation is actually a very broad topic, and I really love this topic because you can study it from different perspectives. You can do simulations, you can do observations, etc. But we don't know much about planet formation because the only good reference actually that we have is our solar system, and it has only 8 planets. It's actually a lot. It's not a lot for me, for my curiosity. And yeah, so today I'll talk a little bit about solar system. I'll tell you what the interesting and general questions that we want to answer. I'll talk a little bit about protoplanetary disks, and I'll tell you about planet formation theories and exoplanets in the end. So let's get started. So as I mentioned, the solar system is our only good reference that we have, and we still don't know a lot of things about solar system, but we know like these things that I'm showing to you right now. We know that we have 4 terrestrial planets close to the sun. These are small rocky bodies: Mercury, Venus, Earth, and Mars. And we have giant planets: Jupiter, Saturn, Uranus, and Neptune, that are located in outer region of the solar system. And some people call them, all of them, gas giants, but this is a little bit of a mistake because actual gas giants are only Jupiter and Saturn, and Neptune and Uranus are more of like these icy balls with a little bit of atmosphere. So yeah, in general, the questions that we want to answer are like, are there in this universe other solar systems, right? So we want to know how common is our solar system. We also want to know the nature of extrasolar planets. We also call them exoplanets. These are the planets in other planetary systems. And about the nature, I mean, like we want to know all of it. We want to know the radii, we want to know the masses, densities, we want to know the chemical composition, right? So, but the more like broader questions that we want to answer is like, how common are Earths, right? So we want to know about the planets that might contain life in it, that might have contained life in it, and we want to know more about habitable planets. So our story begins with this setup. So you have a star, and you have a newly born star, and we know that around the star we have a disk of dust and gas, and this disk is on a flat plane. It is rotating the star, and people were speculating about the existence of those disks because we know that in our solar system, planets orbit the sun in roughly one plane. So, and people thought they might have formed in protoplanetary disks, in the disk of dust and gas, mostly gas. And they were right, actually. So this is very beautiful picture, image of the star Ichiltau, and you can see this protoplanetary disk. And this image was taken by Alma. This is very famous image, and everyone who talks about protoplanetary disks shows this image. Because this is really cool. We have an actual observation of protoplanetary disks, and we have also observations from Hubble telescope, and so we're quite certain about their existence. So yeah, and as I said, in this disk we have dust and gas, and remember that we have a star, and everything is rotating the star. And when you have these little dust grains and you have gas in it, you might think that they might collide, and this will be a really good assumption. And because so what we have actually, so we have these different sizes little dust grains, and what we have is that bigger ones, they slow down, meaning their relative velocity slows down, and smaller ones become faster. So the analogy that I have for you is like if you have a box with big and small balls, and you start shaking this box, you can notice that every time the small balls hit the big ones, it slows down the big one a little bit. And what does this mean? It means that in this initial protoplanetary disk of gas and dust particles start to impact each other, they start to stick. And then there's this feedback of the start, they start to become bigger, have more mass and gravity, and then they get even bigger, and they start to slow down. So eventually, when they have really low relative velocity, they start to merge with each other, and they become quite huge. And what they become, so we call them planetesimals. This is not a planetesimal. This is actually an image of a comet, but we think that planetesimals might look like that. These are kilometer-sized dust grains. So, and when and you might imagine then when we have quite huge bodies rotating the star, so these bodies have gravitational effect, and they might affect things around them. And what happens that there might be a region where the gravity of this object plays bigger role than the gravity of the stars. So don't forget about the star. It's minding its own business, but it's there. And at some point, things that are affected gravitationally by this object, by this planetesimal, they start getting more affected, and then they become something that we call isolation mass. So it's going to be like a really huge mass. And what we actually noticed is that the isolation mass of Jupiter is 10 Earth masses. And this this 10 Earth masses is actually a mass of the Jupiter's core. So yeah, so this is like our how we think the core of the gas giant might have been formed. So this is a really good, cool plot, and really also. So what you see here is, you can see here that this is in x-axis we have time in millions of years, and in y-axis we have mass in Earth masses. And you can see here, just in 500,000 of years, we have these 10 Earth masses here, and it stays roughly the same for all of this time. But so this MZ, this is solid material, this is the planetary core. But this MXY, X is usually hydrogen, Y is usually helium. It is a gas, and this gas, it grows, and it just grows tremendously at some point, and the whole mass of planet just goes tremendously. This is how we think Jupiter might have formed, and gas giants in general might have formed. So they just this is called core accretion. So this core starts have this huge core, roughly 10 Earth masses, starts having this gravitational effect, and gas starts accreting onto it. Yeah, but this is gas giants. What about terrestrial planets? So, and you also, so you can see that actually the timescale is actually good in this model, because we know that protoplanetary disk exists around 3 to 5 million years, and you can see that Jupiter might have formed in like 10 million of years. But this is not the case for terrestrial planets. It takes a long time to form a terrestrial planet. And the terrestrial planets form at about like 100 million years. And this is a really nice simulation. So yeah, what you can see here, you can see this very chaotic dynamic. But look here, we have something like planets forming. And actually, Jupiter is somewhere here. It is like also minding its own business somewhere here. And here we have some protoplanets. So so they right now don't have really large masses. And also you can see here what is happening is some excitation. These objects here, they start having large eccentricities. They're really excited, like I'm excited to talk about planet formation. And this is because Jupiter plays a role. Jupiter is so huge, it has so large gravity, it affects these objects. And this is actually the same thing that's happening with Kuiper Belt objects and Neptune. Neptune affects these Kuiper Belt objects. But the strength of Jupiter is not enough for these things that are forming here. And you can see that planets start forming here. This is actually how we think terrestrial planets might have formed. So yeah, let's wait till the end. Everything clears up here. Yeah, and this is what we have in the end. We have terrestrial planets. So this is really cool simulation. And yeah, I forgot to put credit here, but the simulation was done by Sean Raymond. So yeah, but Jupiter is cool. And it is also cool because we have seen something like Jupiter in other planetary systems. And this is an Arctic depression of 51 Pegasi b. It is the first planet that was found orbiting Sun-like star. It was found by Michael May and Didier Queloz, and they got Nobel Prize in 2019 for that. So And this is type of object that that is actually in the family of hot Jupiters. We call them hot Jupiters. And here's why. Because so what we know is that it is extremely close to its star. It is like roughly 1% of the Sun-Jupiter distance. And hot Jupiters are actually 20 times closer to their stars than Earth to the Sun. So, and the temperature is really high. Yeah. So this is actually really interesting. But they're not the most common type of exoplanets that we have seen. So, yeah, we want to, as I said before, one of the broad questions that we want to answer is about Earth-like planets. We want to know, are there Earth-like planets? And so I'll tell you a little bit about the transits. So the idea is that if you watch the star and for long enough, you'll see some dip in its brightness. And you also want to know that it has, if the star has a planet, you'll see a dip in this brightness because the planet blocks a little bit of its light for you when you watch it. And if you continue to watch, you'll see a dip over and over again, right? And at the same time. So, but the biggest boom was not when people understood that they can do that. This is what we call transiting method. And yeah, the biggest boom was when people understood they can do that to detect Jupiter-like planet. No, it was because people realized that the discovery of transiting planets gave the best opportunity for discovering something like Earth-like more than Jupiter-like, rather than Jupiter-like. And if you measure the transit accurately enough, even though Earth is really small compared to Jupiter, you still can detect something like that. And this was the motivation behind this mission. This is the Kepler mission, really cool mission. And there's this Kepler telescope. You can see light is coming here, and here is the array of digital cameras and some solar panels. This is not really important. But what's important is that it stares at one point and one spot at the sky. And this is critical because if you want to find something like Earth, and by that I actually mean like the same radius, the same mass, and the same distance from the star, and so if you want to find something like that, how often would you like it to get going in front of the star? So the answer is actually once a year, right? And so the chances that you're gonna miss it are higher if you look at different patches of the sky. But if you just look at one spot, for 3 years, that was the original plan for this mission, you might catch something like Earth-like dips, and you might catch them 3 times. So guess what? We actually found planets. Yeah, I'm very sorry for another plot, but this is really cool. So here's the planet size in Earth radii, and this is the fraction of stars that we detected with Kepler mission, with planets having orbiting time between 5 and 100 days. And for reference, Mercury has 88 days. The orbiting time of Mercury is 88 days. So, and what you can see here is that the biggest number, the biggest fraction, 18.6% goes to 2 Earth radii planets. So 18.6% of stars that were detected by Kepler have planets that have radius of 2 Earth radii. This is just really cool. And yeah, and what you can actually see, so here you can see orbital period, and here you can see again fraction of stars, and most of these orbital periods are between 25 and 50 days. And Mercury, the closest planet to the Sun, has orbital period of 88 days. And that's somewhere here, right? So, so what we actually notice is that all these planets are more common out of all that we detected. This is like, if we sum up all these percentages, this is a big number. But what is this? What is actually 2 Earth radii planet? So we actually don't know, because as I said, for reference, we have Earth, which is 1 Earth radius, and we have Neptune, which is 3.8 Earth radii. So we don't really have an idea what kind of planet might be between of them. But we gave those planets cool names because they're so common. So the cool names are super Earths. These are larger rocky planets. They have higher densities, and mini Neptunes. These are smaller gaseous planets, and they have lower densities. And yeah, again, so as I said before, all of these planets are really close to their stars, closer than Mercury. And what we also noticed is that most of these planets have really high eccentricities, but more to that, they also have really high inclinations. This is not really common in the solar system. In the solar system, the planets orbit the sun in roughly circular orbit. So, we, of course, we want to know what is happening here, because is this solar system so special? We don't know. Yeah. So, and we think that some chaotic dynamics might be involved here. So I want to show you another simulation here. So what we actually found from the simulations is that if we have some really big objects and their orbits, they cross each other, things might get really chaotic. So it might come to the point that one of these objects, aka planets, might be ejected from the planetary system. So take a look at that. It's not working. Sorry. Yeah, this is really cool simulation. I'm trying to show it to you. Here. Sorry for that. Yeah, you see that everything is exciting, and you see these large bodies. These are planets in the simulation. Yeah, and this is what's happening. This is really cool. Yeah, you can see that in the end we left with 2 planets, and we started with 3. But what else you can notice here is that you see this is eccentricity, right? you see these planets start having really large eccentricity. So this is what we think might be happening. But yeah, still we have a lot of questions, a lot of questions that we want to answer, and I'm really excited to work in this field. So this is the readings that you can read. Yeah, this is my favorite stuff. These are two classical papers on the planet formation. I added this memoir book because Mike Brown, this professor from Caltech, he has really good course on the science of the solar system. So you might want to check it out. And this is really good, but advanced stuff. So thank you so much.
Great job, Sabina. If you can pull your, there you go. There we go. We're all good already. Great talk. We're going to start with, I'm going to ask you a few questions about yourself because you are the star of this half of AOT. So we want to get to know you a little bit more as well as your science. So the first thing I want to ask you about is what got you into astronomy, like back whenever you were first starting out, what got you into it?
The more like basic answer might be that I started loving astronomy when I was in high school. I started like watching these discovery shows and reading books. So the book by Mike Brown was one of the first books that I read. But what actually made me to go to graduate school was my internship that I had at the University of Cambridge. There I met really cool people. So, and I decided to go to graduate school.
That's really nice. What you said you watched like a lot of Discovery Channel shows in high school. Which ones? Do you have like a particular one you liked?
Oh, so basically that I'm from Kazakhstan, and that time I was learning English, and I watched all these BBC and Discovery channels because every show was in English. So I was trying to become more familiar with English there, and that's why I was watching like everything that they had. But they had like so yeah, I don't really remember the names, but I remember there was a show called Cosmos. There was definitely a show by Neil deGrasse Tyson.
Probably was Cosmos, yeah, because that's
maybe that was Cosmos.
That's hosted by NDT, so yeah, probably that one. So I know that I mentioned that you also write music as well as doing astronomy. Do you have other hobbies, or would you say that is like your main like hobby that you're really into?
Yeah, music is basically my main hobby because I also play musical instruments. I play piano, guitar, and the drum kit, and it just makes me feel better whenever like I'm stressed out or feel a little bit sad and disappointed. Yeah, so just music is like my way of getting away from this world. But I also love doing puzzles. I'm so in love with Russian literature. So yeah.
What would you say is like your favorite genre of music, if you have one?
So I really love like this indie pop folk music. So I also love country music. I love pop music. But I also like I love writing lyrics. That's why I also more into like lyrical stuff in the music. I really love hearing like good rhymes or like interesting words.
Okay, cool. And before we move to the science portion of the questions, I have to ask you the famous question that we ask every time here at Astronomy on Tap Baton Rouge, and that is, what is your favorite Pokemon? I hope you looked one up.
It's probably Pikachu.
Is that because it's the only one you know, or did you look?
It's really cute.
It is cute. I think that's why he's the mascot. I think that might be the reason. So starting with some science questions, I want to ask you one that you've probably gotten so many times, but I want to hear your answer. Do you think Pluto is a planet, or should it be?
So no, it's not a planet. Yeah, I'm so sorry, but we shouldn't be sorry. So I think Pluto has a really good family of trans-Neptunian objects, so it is in good company there.
All right. Okay. So I can start with some questions from the chat, from the live audience. The first one was a bit of a question about one of your slides. There was a plot, and it was the one where you're talking about like the Kepler planets and the two Earth radii with like the 18%. They were just asking, does the plot say that like 100% of planets have, or 100% of stars have Earth-sized planets, or more than 100% have smaller radii? I think there was a 100% like on the top left or something.
No. So so let me take a look.
Yeah, you can show it if you would like.
No, actually, the top of the plot is 25%. So yeah, as I mentioned, the highest number there was 18.6%, but and Kepler detected like 4,000 exoplanets, but not all of them like these mini Neptunes or super Earths. They're more common, but we also have hot Jupiters, right? They also were detected. And they're easy to detect because they're bigger.
Yeah, I was going to ask if it was true. I kind of heard that hot Jupiters were maybe more common than we originally thought. I was going to ask if you thought that was true, or if it was more of an observation bias.
So yeah, so probability to detect something like hot Jupiter is definitely bigger because yeah, it is better detectable. But and the dip that it will give actually, like with all its mass, and most of these hot Jupiters are even bigger than our Jupiter, so they're like 10 Jupiter masses, and the dip that it will give you is 1%. 1% of it will block only 1% of brightness. So you might imagine that detecting something Earth-like is even harder.
Okay. The next question is from Nikki Purafergan, and they ask, do you find evidence for Planet 9 presented by Batygin and Brown to be solid?
I actually love their symmetry. Yeah, I actually mentioned Mike Brown in the end. Yeah, I was a little bit of a fan of his when I was in high school. So yeah, I read the paper, and yeah, I kind of like I really hope we have ninth planet, but we'll see. They're working really hard on that.
Okay. They have another question as well. They asked, how interlinked are the research of exoplanets and like our solar systems? Like, how interlinked are those two subfields of research of like our planets and of exoplanets?
So first off, we don't actually know much about exoplanets, and the obvious like this interlink might be that if once we know more about those planets, for example, there's a huge research going on to know more about the atmospheres of those planets. We're still like not really certain about that, and we still don't know what their cores are like. Like, we don't know a lot about their chemistry because it's really hard to study that. But yeah, the most obvious interlink might be that once we get this more information, we want to know, are they like planets in our solar system? Yeah.
Cool. And I think there might be just a couple more. We have a question from Stephen Dorsher, and he was very interested in the very last plot from your talk, the animation. And he wanted to know if the eccentricity was really oscillating, or was that time running forwards and backwards? And a follow-up question, if it is oscillating, is that using classical gravity, or does it require GR?
No, yeah. So usually when we study the planet dynamics, we don't go to GR. GR is more of other things. Yeah, so we usually study like this classical mechanics.
Okay. We have a music question for you. It's also from Nikki Profergan, and they asked, do you like Moldanazar Esimdi-Bari? I'm not pronouncing it.
Yeah. So Moldanazar is a famous Kazakh singer. Yeah, I don't listen to his music. I'm so very sorry. Yeah, yeah, I'm more into like kind of this American music. Yeah.
I'm so sorry for butchering those words. And then our last question before we go to our break is from Oscar Fentonez, and they're saying, is it more common for two large terrestrial planets to crash into or to slingshot each other sort of away from the system?
Yeah, like in our solar system, we have 4 terrestrial planets, right? So we didn't really have this like some one of their planets. We didn't really have like encounter towards each other. But as I showed in the animation, so when the like all these little bodies that terrestrial planets are made of, they were like encountering each other, and they like in the end they made protoplanets and planets in the end. So yeah, but 2 planets, no.
No.
not here, at least not here.
Okay. So with that, I thank you so much, Sabina, for being our first speaker tonight. And we are going to go on a break for intermission. And I would like to humbly ask everyone who's watching once again to consider donating to our Venmo and PayPal. And just as a reminder, if you do leave a comment in the memo somewhere letting us know if you prefer Phil Collins or Michael Collins, please also like our video and subscribe while we're waiting. But we will be back at 7:45 to go ahead and have our second speaker. So we're going to take a quick break, and we will be right back at 7:45. Hello, everyone, and welcome back to Astronomy on Tap, the April edition. We are going to go straight into our next speaker and not beat around the bush any longer. But next up, we have another graduate student, this time from West Virginia University. She also writes for Astrobytes and, in fact, also has a deep love for puzzles. And if you go on her Twitter, you can see that she recently completed all 3 of the Ravensburger crypt puzzles, which look very hard from my perspective. And she's here to tell us today about pulsars and how they can be used to detect gravitational waves, much in parallel with our very much beloved LIGO establishment. Here is Haley Wahl.
Awesome, thank you. I'm going to share my screen. Can you all see that?
Okay. Yes.
Okay, thanks. Okay. So hi, I'm Haley. I'm a grad student at West Virginia University and also part of the NanoGrav collaboration. And today I'm going to be talking to you about pulsars and gravitational waves and how we can use pulsars as a galaxy-sized gravitational wave detector to look for these gravitational waves. So first I'm going to set the scene. So, okay, picture this. It's billions and billions of light years away. And 2 giant spiral galaxies are orbiting around each other. They've come so close that their centers are swirling around each other. And these black holes are millions and millions of times the mass of our own sun. And as they spiral inward, they get closer and closer, and they radiate out energy into space as they're doing this cosmic dance. And that energy goes into space and is so energetic that it moves space-time itself and it ripples space-time. And so it's compressing and stretching space between galaxies, between stars, between planets. And here on Earth, on a bunch of different continents, we have scientists that are sitting at their computers using supercomputers and looking at tens of years of data from these cosmic lighthouses that have given off little blips of radio waves, and they're analyzing all of these radio waves and trying to look for exactly that signature of those black holes that I talked about. So welcome to the world of pulsar timing. So gravitational waves, which are the energy that I mentioned earlier, are ripples in the fabric of space-time produced by very large masses. So they can be black holes, neutron stars, they can be a black hole and a neutron star merging, or kind of anything that's just really, really massive and anything that gives off a lot of energy. So gravitational waves were first detected using LIGO. So in 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected gravitational waves from 2 black holes that merged 1.3 billion light years ago. So this is one of the detectors, and there are 2. There's one in Washington and one right there in Louisiana. And so how LIGO works is it's what's called an interferometer. And so you have a laser source that produces light, and it travels to 2 arms that are about 2.5 miles long each. And so first it has to travel through a beam splitter, which splits the light in 2 and throws half of the light to one arm and half of the light to the other. And that light will bounce off a mirror and then eventually will come back together at this light detector. And so the way that these arms are set up, each of them is exactly the same length. The light will bounce back and hit the light detector so that they're what's called out of phase. And so that basically means that the crest of one wave will be exactly in line with the trough of another. So they'll cancel out. So it's like taking a really big positive number and adding it to a really big negative number. You're going to get 0. But when a gravitational wave comes, it's going to stretch and squeeze the arms by just a little tiny bit. And these things are so precise that it can pick up anything. So you're going to change the length of the arm by just a tiny, tiny bit. So these waves are going to be slightly different than this, and they're going to be slightly more in phase. And so you're going to get a signal here because these won't exactly cancel each other out. So it's like taking negative 150 and adding it to 200. You're not going to quite get 0. So you're going to get a signal here. And that's how LIGO detected the first gravitational waves. So the first signal looked like this. So it's really kind of hard to see here with the yellow. So the yellow was the predicted gravitational wave signature, and the orange was what they saw. So these events were very, very quick. So you can see this is just a fraction of a second. And this was a black hole merger. So on the y-axis here, we have strain, which is just essentially how much the space is stretched and squeezed by the gravitational wave. So you had one event at the Hanford detector, and then you had another one in the Livingston one, which is in Louisiana, and they were slightly delayed, but because they're in different places, but when you match them up, they look exactly the same. So that's how the detection was made. And since then, LIGO has detected about 50 events since then. So a lot of black hole mergers, a neutron star black hole, and possibly some neutron star mergers. Okay, awesome. LIGO detected gravitational waves. So why do we need pulsars if we already have them? So the answer lies in a comparison between light, electromagnetic radiation, and gravitational waves. So when you can separate out light into all different wavelengths. So you have the radio waves, which are the very low energy, so very high wavelength. You have infrared, visible, UV, X-rays, and gamma rays, which are the most energetic. And these are all given off by very different things. So for instance, radio transmitters will give off radio waves, and X-ray machines will give off X-rays, and really energetic events will give off gamma rays. And so these are all produced by different sources. And in order to detect these, you need different instruments. So for instance, if you look in a telescope in your backyard, which looks at visible light, you're probably not going to see radio waves. And if you use an X-ray machine, you're probably not going to detect something in the infrared. So you need all different instruments to do that. And that's exactly like gravitational waves. So gravitational waves are produced at a bunch of different frequencies, depending on what their source is. So for instance, LIGO, which is a ground-based interferometer, can detect things like neutron star mergers and black hole mergers, which are really energetic and have a very high frequency of gravitational waves. Space-based interferometers, which is basically like LIGO in space, can detect stellar mass compact binaries and supermassive black hole mergers. So the LISA mission is one of the first, and it's going up in the 2030s. And then you have pulsar timing arrays, which detect the less energetic phenomena, such as supermassive black hole binary mergers and primordial gravitational waves, which are gravitational waves from the very early universe. And where you're going to get the pulsar timing array band is about in the nanohertz regime. So that's just the frequency. Again, you have how much the space is stretched and squeezed on the y-axis. And up here with the cosmic microwave background, which is the light from the early universe that has since been stretched as the universe has expanded, you're also going to detect primordial gravitational waves. But here we're going to focus on pulsar timing arrays. So what exactly is a pulsar? So pulsars are extreme objects in the universe. They are rapidly rotating, highly compact magnetic neutron stars. It's like taking something the size of Manhattan, crushing it into the size of taking something the mass of the sun, crushing it into the size of Manhattan, and spinning it as fast as a blender. So these are really extreme. For people that are local to Baton Rouge, a neutron star can fit between the Louisiana state capitol and the old Blue Bayou Water Park. And so a neutron star could fit between there. And so they're really small. For people who aren't local, they're about the size of Manhattan, about 10 to 15 miles in diameter. So they're really not big. They're so dense that a teaspoon would weigh as much as Mount Everest. So it's incredibly compact, so much that in the atoms of a neutron star, you get the protons and the electrons, and the whole atom is squished together to make neutrons. And they're so magnetic. They're 100 million times as magnetic as the Earth. At a distance of the moon, they would wipe out all of the data on all of the credit cards on Earth. So these are crazy extreme objects, and they give off radio waves, and they look like a lighthouse as they spin because they give off this radiation along their magnetic axis, which is tilted with respect to their spin axis. And so what they're going to do is they're going to wobble, And we're going to see this beam of radio waves as it passes along our sightline. There are two different types of pulsars. The first one is a normal or canonical pulsar that has a spin period of about 0.5 to about 20 seconds. And these are born in supernovae explosions. So when a really massive star, anywhere from about 20 to probably 50 times the mass of our sun, starts to fuse iron in its core, it can no longer generate energy to counteract that gravitational pressure that's pulling it in. And so it's going to collapse and it's going to go supernova. And what's left behind is a really dense core. And if that core has if it's spinning a certain speed and if it has a certain magnetic field, it'll become a pulsar and start radiating radio radiation. But then you also have millisecond pulsars, which are recycled pulsars. So as a pulsar spins, it's going to lose energy because it's radiating away mostly radio waves. And so it's going to spin down and it's going to lose energy. And eventually it's going to stop spinning. However, if it has a companion, something like a main sequence star, if it's in a binary, which just means two stars orbiting around each other, it'll steal mass off of that companion and it'll start to spin it up. So it's like an ice skater pulling her arms in, or pulling their arms in. So as the mass gets closer and closer to the center, it's going to conserve angular momentum and it's going to spin up. And so that's going to create those really, really fast spin periods. And those spin periods are incredibly stable. They're some of the most stable clocks in the entire universe, and they rival atomic clocks in terms of precision. And so they're incredibly good timekeepers, and that makes them really useful scientific instruments. So what pulsar timing does is it looks at when those radio waves arrive at Earth. So because they're such good timers, because we can measure their period so accurately, we can predict exactly when the light will get to us, and we can predict it down to nanosecond precision. So if a gravitational wave comes between us and the pulsar, it's going to change that time of arrival. It's going to change, when the pulse gets to us. So for instance, if the gravitational wave is coming toward us, it's going to compress the space between us and the pulsar, meaning that the light from the pulsar is going to have to travel a smaller distance. And so we're going to see the pulse earlier. But if it's moving away from us, then the gravitational wave will stretch the space and it'll arrive a little bit later. And so by looking at all of these pulsars, we can try to determine whether or not a gravitational wave has passed between us and the pulsar. But these gravitational waves are very low energy, and so it takes a really, really long time to get all of these pulsar signals and to look for these gravitational waves. So the key to gravitational waves and pulsars relies on the difference between the time that we detect and the time that we predict, and that's called the residual. And so it depends also on the angle between pulsars in the sky. So two scientists, Hellings and Downs, did a study and found that the angle between the pulsars in the sky, so this is just how much the pulsars are separated in the sky, and if you look at that compared to the arrival time correlation, which basically looks at the difference between, the model, when we predicted the pulse will arrive and what it actually does, if you look at that and you map it against the angular separation, you'll get this curve. And so if we have pulsars all around the sky up to 180 degrees apart, and we get these correlations, then we can see, and we do have this curve, then it's a pretty good indicator that gravitational waves have passed through the system. And so our local organization that's trying to detect these gravitational waves is NanoGrav, which I'm a part of. It's the North American Nanohertz Observatory for Gravitational Waves. Going back to that frequency, they are detected in the nanohertz regime. So NanoGrav was founded in 2007. It consists of over 100 members at 40 institutions across the US and Canada, and it monitors about 50 pulsars all around the sky to try to look for these signals. So it uses these 4 telescopes mainly So first we have the Green Bank Telescope in West Virginia, which is the largest steerable radio telescope on the planet. Then we have the Chime Telescope in British Columbia, Canada, which has kind of a strange shape. It kind of looks like half pipes, but it's really useful in especially detecting fast radio bursts, but also looking at pulsars. On the bottom right, we have the Very Large Array Telescope in New Mexico, which also times some pulsars. And by times pulsars, I just mean basically monitors them to get the time of arrival. And then we have Arecibo, which is faded out because unfortunately Arecibo is no longer with us, but it gave us some really good data for a really long time to help us try to detect gravitational waves. And we also have the International Pulsar Timing Array. There are timing arrays around the world. So we have the North American one. There's also a European pulsar timing array that has telescopes in Germany, England, Italy, kind of all over the place. There's the Meerkat telescope in South Africa, which is part of the South African pulsar timing array. We have a couple in India. The Indian PTA uses them to time these pulsars. And you have FAST in China, which is a really big radio dish. Then you have the Parkes Pulsar Timing Array in Australia that looks at a lot of different pulsars. And so, again, these gravitational waves are really low frequency. And so it takes a really long time to detect all of these gravitational waves. And the advantage of having telescopes all around the world is that telescopes in the Northern Hemisphere can't see all of these pulsars. They might just be too far south in the sky. And so if you get other instruments in other parts of the world, then you can combine the data and get more pulsars and really try to nail down that Hellings and Downs curve. So have we found anything yet? Maybe. We are currently we just released our 12.5-year data set. So we took data on about 50 pulsars for about 12.5 years, and we found a really strong signal in the data. And we can rule out some noise sources, but not all. So basically, it may be a gravitational wave, but maybe not. We haven't really ruled out everything yet. So definitely look forward to more data. We're analyzing our 15-year data set right now to try to figure out if there actually is anything in that data. So what's next for pulsar timing arrays? More data, of course. Unfortunately, we lost Arecibo, but we have been doing a lot more timing with the Green Bank Telescope and with Chime and with the Very Large Array. Hopefully, we can combine our data with other timing arrays around the world to see what we can find. Take the strongest pulsars from all around the world and combine that data and get really high sensitivity. And we're also always looking for more pulsars using pulsar surveys. So basically, what that does is it takes some telescope like the Green Bank Telescope, and it will just scan the sky and just look for pulsars. And so we're always looking for more to add, because more pulsars means differences in angular separation, which can help nail down the Hellings and Downs curve. So it's a really exciting time to be in gravitational wave astronomy and in pulsars. So that is the end of my talk. Thank you so much. If you want to find out more about pulsars, I do Pulsar Fridays on Twitter. So different pulsar topic every week. So feel free to follow me, and thank you.
All righty. Thank you, Haley. Awesome talk again. Both of our speakers have awesome talks. They always do. So I wanted to also start with some questions about you as well. And the first question is actually something you just mentioned. You've been really active on Twitter lately, making science threads and talking about pulsars. And I want to know what you think, what in your opinion is so important about doing science communication on a platform like Twitter.
Yeah, so Twitter reaches a ton of people, and you can reach people across the globe really instantly. And so I think that's great. I also love pulsars. I think they're such cool objects. I could go on for hours about just pulsars themselves. And so teaching people about something that, is not really talked about is really fun. Like teaching people facts like the first exoplanet ever found was around a pulsar. I think that's kind of a fun one. So that's really important. And just, science is so cool, and I just really want to share it with people, and people seem to engage with that, and it's really fun.
Do you think it's like important for like a scientist to be able to communicate their science in that way? Or is it just something you do because you like doing it and you think like your field interests people, I guess?
Yeah, so astronomy is definitely one that can reach a broad audience, but I think that being able to communicate your science is a really useful skill, not only for, public talks like this, but for funding agencies. It's really good to be able to explain your science simply if you want to get, a grant. But it's also just fun to teach people about things that not a lot of people know about. And pulsars is a fairly small field, so I'm not sure that a ton of people are doing science communication in pulsars. Nanograv does do a lot of outreach, but I just think it's fun to share cool things about pulsars that I think are cool.
Alrighty. There was a question in the chat that I normally ask sort of in this section, so I thought I would just go ahead and ask it. What does a normal day of work look like for you as an astronomer?
That's a good question. As a graduate student, it definitely varies. I know a lot of people have a lot of Zoom meetings in COVID, but it was kind of the same before. In Nanograv, we have a ton of different working groups. And so there are people that work on pulsar timing. There are people that work on the detection side. We have public outreach. And so I'm on a lot of telecons. Again, every day is different. Sometimes I'm writing and submitting papers. Sometimes I spend the entire day, installing software and don't get anywhere. But it definitely varies. Sometimes I get to do cool things like meet with people around the world. Those meetings are usually really early in the morning, but it's really fun to be on a telecon with, colleagues from Australia and Europe. And yeah, it definitely varies every day.
Okay. I also wanted to ask you sort of a question that is new, but I think could be interesting. Is there a specific person that you think like inspires you scientifically, or like something that inspires you specifically in science, that is?
Yeah, I think definitely my mentors have inspired me quite a bit. I went to the University of Vermont for my undergrad, and I kind of went in just knowing that I wanted to do astronomy research, and there happened to be one person there that was doing astronomy research at the time. And so that was Dr. Joanna Rankin. So I'm like, hey, can I do research? And she said yes. And she just became this amazing role model, and she's just this amazing person. And she, basically came up with the theory of pulsar emission and kind of wrote the book on pulsar emission, and has just been just kicking butt for, tens of years and just doing amazing things in the field. And just, as a female role model, she has really inspired me to just keep going and to never give up. And my current mentor, Dr. Maura McLaughlin, is also an amazing scientist and just an amazing person. And she is really big in the field and has just really inspired me to just keep going. And there's nothing, in the field that you can't do.
Alrighty. Awesome. And then before we move into our science questions, I want to ask you again, who is your favorite Pokemon?
My favorite Pokemon is Jigglypuff. That's for you, Kate.
All right. So let's get started with some science questions. And there are quite a few in the chat. Our local audience loves gravitational waves and loves LIGO. As you can probably guess, considering Livingston is like less than an hour away. So definitely a lot of questions there. But the first question, it was kind of answered within the chat, but I thought I would field it to you anyway. And it's from Fred Sunderman, and he's asking, this may be an odd question and they're not questioning gravitational waves, but could something else have produced the same sort of waveform that LIGO detected as its first gravitational wave?
That is a very good question. I'm not super familiar with LIGO data, and so I'm not quite sure. But if it's anything like Nanograv, then they've done the modeling. They've done, a ton of different independent things. I know they check the LIGO data a lot, and just various teams verifying it. And so in order to announce that detection, I believe they did a lot of work and consider all of the options and wouldn't have, produced that result unless they were really confident in it.
Okay. The next question is from Rob Parks, and I'm going to add some context that wasn't in the question, but since I know this person, I think I know what they mean. And they were asking how a gravitational wave signal differs from an exoplanet signal. I think they mean specifically in the radio, like in the radio telescopes, when you would be looking at what's the difference between like a pulsar signal and an exoplanet signal, I think is what the question is.
So like a gravitational wave signal over time versus a planet signal?
Yeah, I think from like the radio aspect.
Okay. So with these gravitational wave signals, especially in pulsars, they're not going to be something that you get instantaneously and just automatically say, okay, hey, boom, and pinpoint the, 0.2 seconds that a gravitational wave came. So these pulsar signals, you really need to add up the signals over time. And you need a really huge amount of data. So again, we're on our 15-year data set. And so you're not going to notice data, and you're not going to notice a gravitational wave signal with just, one pulsar and looking at it for a little bit. So I think the answer to your question is that a planet signal is very quick, whereas a gravitational wave signal in pulsars takes a really, really long time to add up.
Okay. The next question is from Oscar Fentonez, and they're asking, would it be possible for us to somehow generate energy from the gravitational waves that we receive on Earth?
So the gravitational waves that we receive on Earth, especially the ones that we detect with pulsars, are so low energy and they've traveled, probably billions and billions of years. And so they're really low energy. And so my guess would be no, we probably can't use them for energy, but that is a really interesting question.
Alrighty. The next question is from Nikki Purafergan, and they're asking, what kind of objects generate gravitational waves that are detectable by pulsar timing arrays?
Yep. So the objects that will generate gravitational waves or that pulsar timing arrays will detect are black hole mergers or supermassive black hole binaries are going to orbit around each other and emit these gravitational waves as they do, and just really massive objects and things that take a long time.
Okay. And then I think the last one, I may be missing one, but the last one from our audience is from Stephen Dorsher, and he asks, do the correlations in space of the pulsar signal depend on unknown factors in the universe, such as conditions like the anisotropy in the CMB and other sort of exotic universal conditions?
Yeah, that's a good question. When we're looking at, I'm going to try to answer this. When we look at pulsar timing data, we have so many things that we need to account for. So we account for everything from the scattering that the light from the pulsar does when it goes through the interstellar dust, when it goes through the interstellar medium. We have all kinds of models with that. We even have to get the exact positions of the planets, because you need to look at the gravity and figure out exactly when the time the pulsar signal will get to us. So, we had a couple of years ago, the massive Jupiter was off. And so everything was kind of messed up. So it depends on a lot of factors. And we do try to keep all of those factors in mind and get our models as precise as possible. So I don't believe the anisotropy is a factor. I'm not 100% sure, but anyway, we do account for a lot of things in our models, everything that we can think of.
Okay. And then I wanted to ask you one more question because, I can do that because I'm the MC. I wanted to ask you, how easy is it? I assume that, since you are at West Virginia and you are close to Green Bank, then it's really easy for you to get involved in nanograv. Is it as easy for other people to get involved in the nanograv collaboration if they're not in places like that? And then sort of a similar-ish question, does the nanograv collaboration work closely with LIGO, or is it more so like its own thing where you're doing sort of your own gravitational wave detection?
Yeah, so I'll answer that first. That second question first. We don't work with LIGO. Some people in nanograv have before worked with LIGO, but the gravitational waves are from such different sources that they're totally different instruments. So in general, no. But we do look to LIGO. It's a big scientific collaboration. Nanograv is a little bit smaller, but yeah. So your first question, if people can get involved in nanograv, we have a huge outreach program. If there are undergrads that are interested in nanograv, we have all kinds of programs. We have STARS, which is the undergraduate telecon, and I think that even if we also have the Pulsar Search Collaboratory, which is a group which is for high school students, and high school students can get involved with Pulsar data. And so that's run partly through nanograv. My advisor, Dr. Maura McLaughlin, actually runs that. And so it's really easy for especially younger students to get involved. But in general, yes, we always share all of our data and we do a lot of outreach. And so definitely, if you're interested in getting involved, definitely email me.
All right. Okay. So I want to bring back our first speaker, Sabina, if you want to just like turn your camera on. You don't have to. But I just wanted to go ahead and thank both of you very much for an awesome show tonight and for graciously volunteering to come speak with us. We are always really happy to have you guys, and we know you're both really busy. I also wanted to give a small shout out to our streamers, Allie and Alex, who are behind the scenes, and all the rest of our AOT staff. Everyone works really hard to put this show on for you guys, and we always love to have it. So before we head out, just a few last minute things, and a lot of them you've heard before. If you're watching us asynchronously and not live, feel free to still interact with the video in some way. You can leave a comment, like the video, reach out to our social media, all that fun stuff. Please subscribe to our channel. It really does help us out. And also please consider donating if you feel that like you want to. So keep an eye on our Facebook, our AOT Facebook, our Instagram, and our Twitter. We post about all our events as soon as we know about them, as soon as we have information. And we will hopefully see all of you here on YouTube again next month, where we'll have 2 more lovely speakers for all you guys. Until then.